In the previous video, we looked at computing double integrals over rectangular regions. Now we would like to look at double integrals over more general regions in the plane. So we're going to start by looking at computing integrals to find area of certain types of regions. This first region is going to be defined by x being between a and b, and y being between two functions, g1 of x and g2 of x. So essentially, we have a function g1 of x that is defined between a and b. And we have another function g2 of x that's defined between a and b. And so the rectangular region is between those two functions extending from a to b. And then the question becomes, how do we find the area of this region? Well, from single variable calculus, we can recall that this is the integral from a to b of g2 of x minus g1 of x. It is the area between those two curves, g2 of x and g1 of x, from a to b. But now we can use the fundamental theorem of calculus to rewrite this g2 of x minus g1 of x as an integral from g1 of x to g2 of x. And we're just integrating dy. Because if we integrate the inner integral dy, then when we evaluate that, we should just get g2 of x minus g1 of x. So this is a way to rewrite the area of a region using a double integral. And this type of region we're going to call a region of type 1. There's no reason that we're going to label this one in particular type 1, but that is the convention that we're going to use. Now, let's look at a region where x is between two functions, h1 of y and h2 of y, and then y is between c and d. So here I'm going to draw one function. Let's call that function h1 of y. Another function I'm going to call h2 of y. Okay, and then I'm going to cut us off so that we're staying between y equals c and d. So again, I want to find the area of this region. Well, we can again use our knowledge of single variable calculus to write this as an integral. This is an integral from c to d of the function h2 of y minus h1 of y dy. And then similarly to what we did before, we can rewrite that difference, h2 of y minus h1 of y, using the fundamental theorem of calculus as an integral from h1 of y to h2 of y of just dx. And this we're going to refer to as a region of type 2. So essentially, we have these two different regions. One we can think of as being bounded by two functions of x. Okay, that's the region of type 1. The other one we can be thinking of as bounded by two functions of y. That is a region of type 2. Now, of course, not every region of the plane is going to be of type 1 or type 2, but we can integrate a function f over general two-dimensional regions by considering integrals of one of those two forms, okay? either this one or this one. Okay, so what are we going to do with the more general regions? Okay, so let me draw something that's a little bit more general. I'm going to go ahead and let it be flat on this side just to make it easier, although it doesn't need to be. Okay, then I'm going to draw something that's like this, that curves about. And then something that curves down here like that. Let's make this a little more smooth. Okay, so this region is neither a type 1 nor a type 2 region, but what I can do is I can split it into a type 1 and a type 2 region. So I can find some point, I'll call this point Z, and I can split this into two regions at the point Z. And that first region, D1, okay, that's between A and Z, and D1 is a type 1 region. And then I can think of, and this is where I might need to change this curve just a little bit where I've made a mistake. But I can think of, there we go, D2 as being a type 2 region. So here we can see when D is a type 1 region, we have a function of x here, and then a function of x here. Okay, and we're looking at the area between those two curves. But on the other side, we can think of the type 2 region as being this function of y minus that function of y. So in essence, we can turn every one of these general regions into a finite number of type 1 and type 2 regions. Okay, now that we have these more general regions, let's look at a couple examples. Our first example says, let D be the region bounded by the parabola y equals x squared, the x-axis x equals 0, and x equals 1. So I'm going to draw y equals x squared. And then I know it's bounded by the x-axis, x equals 0, which is just the point there, and then x equals 1. So that's going to be my region. I'm going to integrate over. I'm going to call that region D. And now I want to evaluate that integral. So I have to describe that integral. I'm going to think about this as being a type 1 region. Okay, so this goes from an integral from 0 to 1. And then an integral that's between two curves. Those curves are y equals 0, which is the x-axis, and y equals x squared. Okay, so I'm going to be between those two curves for this type 1 region. Now, I'm trying to not just find the area of that region, I'm trying to integrate a function over that region. Okay, this integral, because it's a type 1 region, is going to be dy, okay, because I'm between two curves, y is a function of x, and dx. Okay, let me be explicit that this is the function y equals x squared, and this is the curve y equals 0. Okay, now it's just up to me solving this integral. Okay, so I'm going to integrate that function dy. The antiderivative of x squared, which is a constant, will be x squared y. The antiderivative of 2xy, okay, well, the 2x is just a constant. Okay, the antiderivative of y is 1/2 y squared. So that's going to give me xy squared. You can take the derivative of that and see that the derivative with respect to y will be 2xy. And then finally, I'm going to subtract the antiderivative of y squared. But now I'm realizing when I worked out this example, I had changed it just ever so slightly to 3y squared. So in fact, this is going to be the integral of 3y squared, which is y cubed. Now I need to evaluate that between 0 and x squared dx. Okay, so now I have the integral from 0 to 1. And let's see, x squared times, and then y is x squared. That's going to give me x to the 4th plus x times y squared. Y squared is going to be x to the 4th in this case, so I'm going to get x to the 5th. And then y cubed, that's x squared cubed, or x to the 6th. I'm going to integrate all of that dx. That's going to give me 1/5 x to the 5th plus 1/6 x to the 6th minus 1/7 x to the 7th. That's all going to get evaluated between 0 and 1. So essentially I have 1/5 plus 1/6 minus 1/7. Okay, so if I find a common denominator, that is going to end up being 47 out of 210. Okay, so that is a double integral over a general region that's basically a type 1 region. Okay, our second example says a park is enclosed by 2 fences that follow curves y equals square root of x and y equals x squared. If the density of mosquitoes in the park is given by rho of xy equals 1 plus 2xy, 1,000 mosquitoes per meter squared, find the total number of mosquitoes in the park. So first I need to draw this park. That's y is equal to square root of x. Then y is equal to x squared. So it makes this interesting shape. Those curves clearly do intersect at the point 1, 1. Okay, now I'm going to describe this. I can describe this one actually very interestingly as either a type 1 or a type 2 region, but because these functions are already written as y equals square root of x and y equals x squared, I'm going to go ahead and think about it as a type 1 region. So this total number of mosquitoes is going to be the integral, because I'm going to integrate the density of mosquitoes. So it's the integral from 0 to 1. Okay, that's the limits that I have in x. And then the y limits, it's between the two curves, x squared and square root of x. Okay, so I'm finding the area, okay, between square root of x and x squared. Okay, that's this region right here. Okay, I want to integrate that density. That density is 1 plus 2xy dy dx. And now I want to do that integral. So I'm going to integrate. So I will get the antiderivative of 1 dy is going to be y. And then the antiderivative of 2xy dy is going to be xy squared. I'm going to evaluate that between x squared and square root of x. So when I substitute in I'm going to get square root of x plus x times y squared. So that's x times x, or x squared. Okay. And then minus y is equal to x squared. And then x times y squared, that's going to be x times x to the fourth, or x to the fifth. Okay, I'm going to notice that the x squareds here cancel. It's kind of nice. So I'm going to integrate square root of x. Okay, that's going to give me 2/3 x to the 3/2. And then minus, okay, the antiderivative of x to the fifth is 1/6 x to the sixth. Evaluating that between 0 and 1. So this is equal to, in fact, 2/3 minus 1/6, or 1/2. Okay, so we have 1,500 mosquitoes here in this park, if that's the density, okay, or 500 mosquitoes.